Okay, today we're going to be talking about linear and quadratic modeling. And the first thing we're going to talk about is how to determine whether a function is a polynomial function or not. And basically, to make it very simple, the idea here is twofold. First of all, a polynomial cannot have a negative exponent, so no negative exponents. And then the second thing here is that it cannot have any fractional exponents. So for instance, something like 3x to the negative 2 would not be a polynomial because when you move this to the bottom, it's 3 divided by x squared. So this is not a polynomial. If you have something like 4x plus 17x cubed, now both of these are terms that make a polynomial because you have x to the first, that is a non-negative integer. So let me underline that. A non-negative integer. Non-negative meaning it can be 0 or bigger than 0. All right. And so 3 is a non-negative integer, but as soon as I add a plus square root of x, that makes this entire function not a polynomial because this can be rewritten as x to the 1/2. So the two things that you want to look for is any fractional exponent makes it not a polynomial and any negative exponent makes it not a polynomial. So let's see how this works on a couple of sample problems. Okay, which of the following are polynomial functions? For those that are polynomials, state the degree and the leading coefficient. For those that are not, explain why not. Okay, here we have 4x to the third minus 5x to the first, and I'm going to go ahead and add 1/2 x to the 0. The reason is because anything to the 0 power is 1. 1 times 1/2 is simply 1. So 1/2 times x to the 0 is the same as simply just 1/2 times 1, or just 1/2. I write it here so that you can identify the exponent as being a non-negative. 0 is not negative. Here you have a 1, that's non-negative integer, and we have 3. It's also a non-negative integer. So yes, this is a polynomial, and it is of degree 3. The degree is the highest exponent out of all of these that you have listed. So the degree is 3, and the leading coefficient is the coefficient or the number that is in front of the term that has the highest exponent. So this would be a leading coefficient of 4. Okay, let's go look at part B. Is this a polynomial? No, it is not, because we see a negative exponent. So automatically you will say no, and it says if it's not, explain why. You'll say because of a negative exponent. Let me actually write that out. Negative exponent. All right, let's look at letter C. Here we have the square root of 9x to the fourth plus 16x squared. So I can write this as 9x to the fourth plus 16x squared, all of this to the 1/2 power. Now, we see the square root here, and that automatically makes it not a polynomial. So you would say no, and it's because of a fractional exponent. Now, I want to caution you on something. You have to be careful here. First of all, this square root cannot be distributed to both of these terms. So it can't be 3x squared and 4x. If you take the square root of 9x to the fourth, you do get 3x squared. You take the square root of 16x squared, you get 4x. But this is not the proper way to evaluate this square root. Let me prove it to you. Let's say you have the square root of 9 plus 16. We all know 9 plus 16 is 25. The square root of 25 is 5. We know that that is the right answer for sure. But if you take the square root of 9 separately and make it 3, and the square root of 16 separately and make it 4, you get 7. And 7 is not equal to 5. So you have to be very careful not to do that. When you can do it, however, is when you have things that are being multiplied. So if you had 9x to the fourth times, let's say 25x squared, because these are multiplying, you could do 3x squared times 5x. So I want to make sure that when you are multiplying, there's certain things you can do, but when you're adding and subtracting, there are certain things you can't do. All right, letter D. Is this a polynomial? Yes, it is, because we have an x to the first, x to the fourth. These are both non-negative integers, so the degree is the highest exponent. That's going to be 4, even though it's written out of order, and the leading coefficient is going to be -2. Make sure you use the sign and the number. All right, here we have something that we learned in Algebra 1 and Algebra 2. We just want to write a simple equation of a line that goes through these points. F of -1 equals 2, which means the first ordered pair is -1, 2, and the second ordered pair is 3, -2. In order to do this, we're going to use the point-slope formula. We call this formula the point-slope formula because you need two things in order to use this formula. You need a point that the line goes through. We have two of them here, so we're fine there. And we need the slope, m, between these points. That's what we don't have. So for that, we go to another formula that we learned in Algebra 1, which is the slope between 2 points. So it's y2 minus y1 over x2 minus x1. You've seen this before. So let's go ahead and figure out our slope. Our slope is going to be -2, this y, minus this y, which is just -2, over 3 minus a -1, which I'm going to make plus because you have a minus and a minus back to back. So you have -4 over +4, -1. So our slope is -1. Now we can choose either this ordered pair or that ordered pair as our x1 and our y1. So I'm going to use this first ordered pair. Either one will give you the same answer. So y minus 2 is equal to the slope, m, which is -1, x minus a -1, which is going to make it a +1. And we can either leave it in this form or we can distribute. Let's go ahead and distribute here. -x minus 1, add 2 to both sides. And so our final answer comes out to be y is equal to -x plus 1. And essentially that's all you have to do in order to write the equation that goes through 2 points. All right, here we have Camelot Apartments bought a $50,000 building. For tax purposes, they are depreciating it $2,000 per year over a 25-year period using straight line depreciation. What is the rate of change or slope of the value of the building? So how much is the building changing by as time is changing? That's basically what rate of change means. Well, it's given to us right here. Anytime you see the word per, you know that that is going to be a word that represents rate. So we know that this is going to be changing at, let's just say, $2,000 per year. So that is the rate of change. Write an equation for the value v of t of the building as a linear function of the time t. Well, the value of the building at any time is going to be its starting value, 50,000, minus $2,000 per year t. So that makes sense. If t is 0, then the building is worth $50,000. After 1 year, it's 50,000 minus 2,000 times 1, which is 48,000. It goes down 2,000 a year. So that's what we want to have for that. So v of 0, we just basically said, that's going to be 50,000. Oops, let me write that a little bit better. 50,000 minus 2,000 times 0. That's just going to be 50,000. And then v of 16 is going to be 16 years later. So 50,000 minus 2,000 times 16. That's going to be 50,000 minus 32,000. That's going to be $18,000. So that would be how much the building is worth after 16 years. Okay, here we have the we have a table of values, and in this table we have how much this particular company priced their cereal at that week and how many boxes of cereal they sold in that week. So we can see that as they raised the price of the cereal, the number of boxes that they sold went down. And the question is, what could we predict? Could we use this model or this data to predict what would be the sales if we dropped the price to $2, made it real cheap, or if we raised it to $4, what could we predict that the sales would be? So in order to do this, we need to do a linear regression on our calculator. Okay, from the main screen, by pressing on, you're going to hit 1 for new document. And once you hit that, it's going to say, do you want to save any unsaved? No, you don't. And you want to add lists and spreadsheet. And so in this column here, you are going to type in the word price. And here you'll type in boxes sold. And you will start to input your data. And so here we have 2.4, 2.6, 2.8, had to change my calculator from exact mode to approximate, and 3, 3.2, 3.4, 3.6. All right, so now we're going to enter in the number of boxes. So that's going to be 38,320 and 33,710. And then we have 28,280, and then 26,550, then 25,530, and then 22,710, and the last one is going to be 18,260. And then from there, we're going to hit menu. We're going to go to statistics, stat calculations, and we're going to do a linear regression. And here we will select prices to be our X and boxes to be our Y. And we hit OK. And here we have the formula that's been given to us. And it's going to be A plus BX. So A is 73,121 and B is negative 15,166. The nice thing about these calculators is the regression equation that it generates, it saves it automatically in F1. So we're going to go here to Document, and we're going to insert a calculator. So now we have a calculator screen. So now if we do F1 of $2, we should get 42,788 boxes sold. If we do F1 of $4, we're going to end up getting 12,456 boxes sold. So we can see that if we raise the price to 4, the boxes sold go down. If we drop the price to 2, then the number of boxes goes way up. Okay, for this last example, we're going to skip example 6 today and do that in class. It's just another regression. It's going to be a quadratic regression for number 6. But before we get to number 6, example 5, rewrite this equation in vertex form and sketch the graph. Here's vertex form. We call it vertex form because we're able to quickly identify what the vertex is. The vertex of the parabola will be the letter H, comma, K. So this will be shifted right or left, H, and then up or down, K. So let's see if we can do that. In order to do that, we have to complete the square. And we know that students do not like completing a square, but it's really not that bad at all. First thing I'm going to do is I'm going to rewrite this so that the leading, that the degree is first, and so the powers of x are descending. And so the first thing I'm going to do is I am going to factor out the number that is common to both of these first two terms. I'm going to factor out a negative 3. That's going to leave me with an x squared minus 2x, and I'm going to leave a blank here, and then minus 5. This is equal to f of x. Now, the process for completing the square is you have to take half of this term. Half of negative 2 is negative 1. Square that number, and you're going to end up getting positive 1. Now, in order to balance your equation, what you have to do is whatever you've added in, you have to also subtract back out. So if I were to distribute this negative 3 in here, let's just see what we would get. Negative 3 times x squared is negative 3x squared. That's check. Negative 3 times negative 2 is positive 6x. Check. Negative 3 times 1 is negative 3. Oh no, negative 3 is not part of the original equation. I have added negative 3 into this equation, so to balance it, I've got to add 3 here. That way, negative 3 plus 3 is 0, and we still get back to this equation. All right? So, make sure that the number you put here you get by taking the number that you factored out, multiplying it in, and changing the sign. All right, so let's see what we have here. Now we're able to factor x squared minus 2x plus 1 into x minus 1 squared. All right, so it's x minus 1 times x minus 1. And you have a negative 3. And negative 5 and 3 is negative 2. So this is my f of x. Let me write that here. This is f of x. So now we can say that this is a parabola shifted right 1 and down 2. That's the vertex. And it is an upside down parabola because you have an a that is negative. So this is going to end up being right 1, down 2, and a narrow upside down parabola. So looks something like this. All right. So you want to practice this. This takes a lot of practice to convert from standard form into vertex form of a parabola.